Hi, my name is Peter Timby, and I'd like to talk to you about astrophysics at the University of Wisconsin. In particular, I'll focus on cosmology, observational cosmology, and computational cosmology, as well as X-ray astrophysics. So our goals are big ones. We have big questions we're trying to address, ranging from trying to understand the inflation process in the early universe to the process of the expansion of the universe, the recent accelerated expansion of the universe, trying to understand the contents of the universe, the mysterious dark matter, and also to understand the location of ordinary matter, the baryonic matter, that is not fully accounted for in the universe. Finally, we're trying to address other questions that may only be understood through cosmic measurements, astrophysical measurements, such as the sum of the masses of the neutrinos, or whether there are additional light relic particles from the early universe. So the tools we have to address these questions are represented by various experiments and projects underway here. We use the cosmic microwave background radiation to get a snapshot of the universe at the earliest times, and also as a tool to look through the evolution of the universe using the imprint of the growth of structure in the universe on the temperature and polarization fluctuations in the microwave background maps. We're also using galaxy catalogs and creating and studying galaxy catalogs that give us a survey of the contents and structure of the universe. In a related way, we use the 21 centimeter line from hydrogen gas, a radio signature that we can use to probe the volume of the universe. And then to understand the various contents of the universe, in particular galaxy clusters, we use X-ray techniques. So I'll say a little bit about the 21 centimeter technique, which is shown graphically in the image behind me. So that's a radio telescope that we helped construct in Western China in a radio quiet zone as a way to survey the hydrogen content of the universe. So hydrogen has a radio line at 21 centimeters. And if you survey at various wavelengths, different frequencies with your radio receiver, you can simultaneously measure the hydrogen from different distances, different redshifts from us. And so this instrument that you see is optimized for surveying large chunks of the universe. And so it's an experiment, so we're still trying to find out how well we can make it work. But if it's successful, it in principle would allow us to survey from the current time back to times before the first stars formed, and understand the formation of structures in that large portion of the universe. A somewhat more traditional way to measure large-scale structure is to use galaxy surveys. And so Professor Bechtel is involved in several surveys which are either ongoing or about to start. So the Dark Energy Survey is one in which has just released a large amount of data which is available for astronomers across the world to use. So there's a galaxy catalog and much more. The data in that data set can be used for studying dark matter on small scales, so within our own Milky Way galaxy. So by looking at the so-called dwarf galaxies, which have a large amount of dark matter compared to the number of stars that they have. So the Dark Energy Survey is ongoing and is addressing cosmic questions, dark matter, dark energy, and so forth. It's a survey with a particular cadence to it. So it takes snapshots of the sky over and over again. Same regions are seen on multiple nights. And so this is a great way to look for transient events, which can be correlated with other transient events seen in the radio or in gravitational waves and so on. The future is in the Beyond the Dark Energy Survey is the Vera Rubin Observatory, which is under construction and will be online fairly soon, so within a year or so. And Bechtel's group is involved in developing the data pipeline, the analysis techniques that will be needed for handling an enormous amount of cosmic data from that. In the X-ray realm, Professor Dan McCammon studies X-rays from astrophysical sources. One of the goals for that is to try to understand where are the missing baryons in the universe. And so it turns out we don't know exactly, but it's likely that they are in the form, or a large fraction of them are in the form of very hot gas that is found in galaxy clusters. So hot gas, in order to study that, you need X-ray techniques, and in particular, you need X-ray spectroscopy to identify the atomic species that you're looking at. And so this technique has been developed here at Madison, pioneered by McCammon's group, a technique called Xray Microcalorimetry. And that's been used in satellite experiments. You need to be in space to see cosmic X-rays. They get absorbed by the atmosphere. And so these microcalorimeters are able to measure the spectrum in a rather simple way. So they absorb X-rays, but they're at very low temperature and have a very low heat capacity, so that a single X-ray can create a temperature pulse that can then be converted into an energy, a measured energy. And with that, you can create a spectrum. So to develop this technique and test it and use it for a number of scientific studies, McCammon's group has flown multiple sounding rocket experiments with a cryostat on board with these microcalorimeters that are built here as well as at NASA centers. So this is a unique opportunity for graduate students to be involved hands-on with a space mission with a sounding rocket experiment. So a cryostat is carefully designed cryostat is loaded onto a sounding rocket to cool the detectors and get them above the atmosphere. This is a 5-minute flight above the atmosphere, so not a lot of time, but it's precious data. And this is a really unique location nationwide for having access to space in this manner. In the future, these same techniques will be used on an upcoming satellite mission that will be launched in the next year or so. Finally, putting all these things together, we have Professor Moritz Munchmeyer, who is developing data analysis techniques for trying to understand the cosmos. And so in particular, he's trying to answer the question, how do we go backwards from surveys of the microwave background radiation or galaxy surveys that I mentioned, or the 21 centimeter surveys? How do you go backwards from that information to inferring something about the initial conditions in the universe, and in particular about the inflation process? Lots of data is coming in, as you can see, and so finding a way to analyze it is his focus. Machine learning is his particular expertise. And of course, machine learning is a big deal these days. What's particularly special about his work is that rather than treating it as a black box, these machine learning algorithms are designed specifically with the physics that he's trying to uncover in mind. So with that, I'll conclude, and I look forward to meeting with you virtually in the near future. Thank you.